So welcome everyone to RASC Halifax Center. This is part of our NEOWISE presentations that we have provided. This is the 5th of 6 that we are going through right now. I did post on the chat piece the addresses for both our center as well as our NEOWISE site. If you choose to look at those, feel free. We'd love to have you explore us and determine whether or not you'd like to become part of us. So please do. It'll also keep you apprised as to what we are doing with respect to our meetings and with respect to NEOWISE itself. As you can appreciate, NEOWISE as a camping experience this year was canceled due to COVID. So consequently and thankfully, the speakers that we had arranged for that event have all agreed to do presentations. The previous 4 are already posted. These are being recorded, by the way, so it will be up on our NEOWISE website as well as our YouTube channel at RASC Halifax if you wish to review this at any point. With that in mind, with respect to NEOWISE, as I said, it was a camping event. It isn't anymore, but there are a couple of things that have always been associated with our camping event, and one of them is our t-shirt. We have to thank one of our members, John Reed, for designing it for us. You too can own one, by the way, if you so choose. You can order it. You can go to our website and it explains to you how you can order it, your own, any color, any size. But here's the design on the t-shirt. I hope you can see all of it. The original theme of the event was March of the Planets, NEOWISE 2020. And the planets look like they're all sort of lopsided, but that is actually the way the planets would have looked on the August 21st to 23rd weekend. And as you can appreciate, COVID canceled is written over it because COVID canceled it on us. But if, like I said, if you would like to order one, certainly go to our website at NEOWISE. And it'll tell you how to do that. The other thing associated with our NEOWISE is our annual center's astroimaging contest. Now, for those of you who are from away, I apologize, but you can't enter. The contest is limited to those Halifax Center members, as well as any Nova Scotia resident. The deadline now for submission is September 11th, so you've got roughly 10 days to submit your photos if you so choose, for those of you that are from the center. I guess I have something special to note. I don't know how many of you have received your latest edition of Sky News, but one of the greatest thrills for me as a president is to apprise people of our members' achievements. And there are 3 in this edition. First, starting with the cover, Tim Doucette's photo of the NEOWISE comet. Tim is from Southwest Nova in Quinnen, and that's his photo on the cover. Secondly, if you go inside and you look at the photo contest that was the annual photo contest, you will see the photo that won, and it's from Jason Dain. And it's at Polly's Cove here in Nova Scotia, just outside of Halifax is where he took the photograph of the Milky Way over the cliffs of the cove. And the third person was Burgess, and his photo is in this section on the photos of the comet from across the country. So there were 3 very prominent Nova Scotians that we're very, very thrilled to acknowledge in this particular session. So I think at this point, we can go forward with our next presentation. And this one is Walk the Solar System. This is a session that I attended. In fact, it was the first session I attended when my husband dragged me to my very first star party. I say dragged because at that point in history, I had no desire to know anything about astronomy. Things have obviously changed. But Paul had presented this to a group of youngsters and to their parents, and I attended as one of the youngsters because I figured I really didn't know a lot and learned a lot from this presentation. Paul has been a longtime member of our center. He has served in many roles, not only as director, but as past president and as outreach chair, which he currently is sitting as on our board. nationally, he serves on the IND committee. I think, oh yes, and one of the other things that he does in a private life, he's also an author. He has published a book of astronomy poems that you could acquire. So it's a lovely thing. And Paul, at every one of our members' meetings, provides one of his poems to us. Very much appreciated. So Paul, the way you and I agreed to do this is it was going to be more or less a discussion between you and I about how do you walk the solar system? Yeah. So when did you, just for a little bit of background, how did you first get involved in outreach? How long ago?
Well, basically community outreach. I was always, my little 40 millimeter, I would show friends and family the moon. But when I became a scout leader, my first year as a cub leader, they introduced the astronomy badge, and I was at a training session and nobody knew, well, how are we going to teach this? Well, to me, it was easy. So over the 2-week training session, I developed a program to help leaders teach astronomy, and I made a couple of little models, and it just snowballed from there. Teaching my cubs over the years different aspects and seeing their blank looks, I developed hands-on materials that helped show different aspects of what I was trying to point out in the night sky. So it started basically as a scout leader trying to help the cubs get their astronomy badge, and I've just sort of gone crazy with it since.
So I understand that you then read Mary Lou Whitehorn's edition of SkyWays, which is the teacher's guide to teaching astronomy.
Yeah.
And you saw something in there, and I'm wondering how you got from there to what you do now.
Well, in Mary Lou's, she had the toilet paper solar system, and I made one out of paper towel. I don't know if you can see that. It starts 5 rolls of paper towel for the solar system out to Saturn, but each of the squares is 10 million kilometers. But as you can notice, the paper won't do so well outdoors. And when I started to get into outreach, I was doing youth camps and summer science camps and that. So I had to figure a way to show the solar system. Also, the first time I was invited into a classroom, I had slides and that. And it was really hard for the kids to grasp the differences in the size of the planets from slides. So I started by making a model of the solar system. Now, I purchased one, at one of the science stores, and most of the planets were almost the same size. And to me, that's really didn't show the differences that I was trying to show to the kids. So I decided to go ahead and make my own. And basically, styrofoam balls, and with the Earth at 1 3/4 inches, I took that as the average size, and then I scaled the solar system. So as Roy is fond to say, on page 22 of the handbook, you have all the information as to the diameters of each of the planets in the solar system. So I divided the size of the Earth into each of those to determine how big the styrofoam ball would need to be. So going around to various stores, I got little ones and big ones, and of course I got Jupiter. So you can go with the different sizes. Now Pluto, I had to sand down because it was too small for the styrofoam balls that were available in the stores. But I was able to get the size difference. You can see with Mercury and Earth, you can do the size difference. And just regular, I tried oil-based paints. They melt the styrofoam. So I had to go with poster paints. And I painted the images. I don't know if you can see the Earth as
Yes.
I'm turning it here. I used NASA photographs from the various exploration satellites to get as accurate an image of each of the planets as possible. And then I varithaned it after it dried, a couple of coats of varathane so I could take it outdoors. Now, originally I just had this is one of those skewer sticks, the eating sticks. So, but the kids just carried this around. but I found that when I walked, okay, the one person would stay at the one spot for Mercury, and then by the time I got to Earth, he was up beside us. So I couldn't point back to say, okay, here's how far we are from Mercury and that. And so I had to figure a way at my first science camp during the summer to be able to station each of the planets so that we could show perspective and distance. So I went with the pool noodles. They're nice foam, about 4 feet long. And I made with garden stakes. I put a piece of foam on, and as you can see, I filled the hole so that you can put the planet in, and this goes into the ground so that we can show the planet in position. So when I'm walking the solar system, I can put this in the grass and at the right distance, and we'll go into that as we move along here. But also, I've got information on these. This is Mercury. I've got the diameter of Mercury, and then on the back, how far it is from the sun in astronomical units and how many million kilometers that works out to. So I've got one of these for each of the planets, and then I can take these out into a field and mark off the distance. Now, once I got the planets, how big is the sun? That was the hard part. And originally, when I just had the planet on a stick, I'd be at the park and I'd say, well, the picnic table is about the size of the sun. And I get this like blank looks, like, what am I talking about? How can the sun be a picnic table? So I figured I've already started with the noodles. So I started to put them together, and with the Earth at 1 1/4 or 1 3/4 diameter, the sun becomes 7 feet 2 inches across. So just under 2 4-foot noodles. And there had to be a way to connect them. So as you can see here, I've got plastic pipe fittings that fit into the middle of the tube, and I connect the pieces so that I can make my sun 7 foot 2 inches across. So I've got a selection of noodles set up, and that can be the sun. And you'll see in the demonstration later as we walk how it looks as compared to the whole solar system. And when I'm at a camp, I can put this up and leave it. And when with the information on the planet sign, people can actually come and walk around and read how far each of the planets are, and look at the planet sticking into the garden stake. And so it can be both a hands-on and a guided tour of the solar system when we do the walk. But these styrofoam noodles for the pool noodles work perfect. They don't cost that much, and they're easy to get and get new ones. And with the sun, I added the information on the front of it. So our star type, how big a diameter it is, and how hot our sun is on average. So information can be attached, and I have solar flares as well. I've cut out solar flares, so I can talk about different aspects of the sun at the same time, even though all I have is pool noodles for my model. So it's very easy to do, not too expensive, time consuming. Usually it takes a couple days for the paint to dry on the styrofoam balls, and then another couple days for the coats of urethane to dry. Basically, yeah. Yeah.
Where did you get the information to be able to paint these balls so they actually look like the real thing?
I went to NASA's images, like Galileo and Cassini, Messenger, all the different probes that went to the various planets. I took those images and I tried to copy them as accurately as possible. You can see with Mars, these are images from the Mars Global Surveyor. So you can see Steris Major, a main feature, Charisium, a major feature. I put the pole cap in as well. And with Saturn, because of the latest Cassini images, I was actually able to put the, I think, 6-sided North Pole. So I tried to make it as accurate as possible. Now, the only thing that's not totally accurate is the rings, because I couldn't find a piece of rubber large enough. It would have to be about 10 times this size to be accurate for the size of the planet. But this gives a good, very thin foam that, and I use toothpicks, long toothpicks to hold it in. And I got the right angle, the angle of the rings onto Saturn. So I tried to make the models as accurate as I could based on what we know from the Cassini and Galilean probes. We have the Great Red Spot on Jupiter, of course, and the equatorial bands and the north and south equatorial bands. So I tried to be as accurate as I could with my models. So, but you can also just put a big letter on each of them. So I could put just a big E for Earth or a big M for Mars. So, I mean, you could be as detailed or as simple as you want. Basically, you start with a base coat. So with the Earth, I did a light blue, got a base coat. With Mars, I did a little like orange brown, and then I filled in the details. So each of the planets is as close to the color that the Voyager and the Cassini and the Galileo images and the Messenger images showed for the various planets.
Your models are quite shiny. Did you do something besides poster paint to finish them?
Yes, I used outdoor varathane, like a deck varathane for putting on decks. I used that, 2 coats of that on it so that they're waterproof, because the dew and everything would wash the water paint. The dew would take the poster paints away. So I varathaned each of them after they dried, and now they're good for being outdoors. Now, my first set of models was, I just had Pluto without Charon, and 2 NEOWISE ago, one of the participants thought it was a candy and ate Pluto and took a big bite out of Earth. So this new set of models I had to remake, but the images I used were the same as before, the Voyager and satellite images from various spaceships. So, but you can make this basically once you scaled it. So get your measurements from the handbook and start. I found that the 1 3/4 is the best size for Earth, and then scale everything from that. That'll put the sun at 7 feet 2 inches. So I think we're going to post the details of the measurements and stuff on later. So, but this is a good scale for Earth because you can get detail, and then the planets are scaled from that. So now you can get Jupiter and Saturn are a little smaller than they should be for the scale, but the proper size styrofoam ball runs close to $200. So economy also fits into the thing. These ones only cost $5 and $6, so they're not too bad cost-wise for making the. I think probably $30 is the cost for the whole, and that includes the noodles, all my styrofoam noodles and everything. Probably $30 for the whole solar system and sun models. So it's fairly reasonable and fairly easy to make. The only problem is garden stakes are only available in late winter because by the mid-gardening season, they're no longer in the stores. So got to get your materials when you can see them. But the pool noodles work great because they're flexible, and you can peg them down so that the wind doesn't blow them away. But you can add whatever features like your prominences and solar flares, etc. you can add to your model. So you can make it as complicated or as straight, simple as possible. And it's visual. That's the best part about it. It's a visual model that you can use to take the next step.
Paul, can I just intercept for a minute?
Yes.
I'm Lori from Victoria.
Hello.
And We have garden centers open all year long, so we have no trouble with that.
Well, okay, I'll send people your way then if they can't find it when they want to build the model. The other thing with as you can see, I have this on a styrofoam block, so I can take it in and have them all displayed in a classroom. And so it can be taken into the classroom if you have something to put them in, so that you can display them all. And when we do outreach at different conferences and shows like Saltscapes and the RV show, I can post them on the table to draw the attention of people. But it's something very easy and straightforward to make. And with the pool noodles and garden holders, it's really fairly straightforward to make. So it's an easy project, and once you get it, then all you need is a really big field. We're going to go into that in just a minute, but it's sort of a progression when I'm doing because I started with just the models, just these on a stick, and then people holding them, and of course, the one that was holding him first got left behind, so he would follow us, and then I couldn't point out the. So I went to the garden stakes because I had to make sure they would position correctly in the solar system so that we could talk about the life zone and other aspects of the solar system.
So Paul, what groups have you, obviously you've done this at Nova East, because that's where I first saw you. You've also done it at the Ketchum-Kujik National Park's Dark Sky Weekend. And obviously to your scout group. Are there other groups that could benefit from something like this?
I had a summer science astronomy camp at Chester. I used them, and that was great at Chester because the facility we were at was on the top of the hill before going down to the harbor. So I had a long straight road, and we were able to walk the whole solar system with the sun sitting on top of the hill and position all of them right down. It went to almost 2 kilometers when we walked out. So, but we could just see the yellow of the sun when we reached Pluto. But the road was straight, which was great because we could go straight down the hill and Pluto. But the average sports field, you can get to Jupiter or Saturn in. And also with the paper towel solar system, this inside a school, the main hallway of most schools, at least here in Halifax, will go to Jupiter. So you can still show with the paper towel solar system, which you can get the information on making that from Mary Lou's SkyWays teacher's guide. So that was my indoor one, but it doesn't work too well in the rain and outside. So I had to go with my models. But it's the main reason I made these. A student or a cub or a beaver can't hold the slide on the screen. But if they can hold this, and you can say, okay, you're Jupiter, or you're Mars, you're Saturn, it makes it interactive. And that's the big thing with this. The more interactive with the people you're presenting to, the more they're going to get out of it, the more fun they're going to have, especially with young people, the more fun. And with the exception of the little girl that thought it was a candy and ate my Pluto on me, these models lasted over 10 years. And I had to make a new set because I had a couple of them eaten. So, but being interactive is the main thing. And having a planet on a stick, you can hand it to someone in a library and we can show like the inner planet system, and then the outer ones, we can have a bit of spacing. So it's a great way to demonstrate what the planets look like, and then you can do all kinds of interactive things. Once the individual is holding a planet, they're focused on what's going on, and hopefully they'll have fun and they'll learn at the same time.
Great. So unless you have anything else to add, Paul, maybe, or if there are some questions before we go to the video that shows Paul actually using these models to walk the solar system. It's about a 16-minute, 50-second video. So maybe we'll just get to the video and then we can do a Q&A afterwards. How's that?
Okay, I see one question from Anne. Most schoolyards will go to Pluto. An average junior high football field or high school football field soccer field is large enough. You have the sun at one end. You can actually walk this demonstration out to Saturn. And as you'll see in the video, once you get to there, there's ways to demonstrate. Unless you have a long straight road that you can walk along safely, basically within a schoolyard, you can get to Jupiter at least, and possibly Saturn. So schoolyards are great. I use them all the time. And in good weather, I'll go out and do the solar system walk, talk to the grade 5s and 6s. I'll do the solar system walk with the models outside if possible. So.
Okay. And with that, we'll get started.
Welcome, my name is Paul Heath. I'm doing the solar system walk. This is part of our NEOWISE 2020 virtual star party. See, I have models of each of the planets in the solar system and our sun. They're to scale. So the planets are this size. The sun will be 7 feet 2 inches across. And we're going to see what it looks like when we reach the distant gas giants as we move away from the sun. Now, when we measure the solar system, we have to have a stable unit. And what we do is measure the distance from the sun to the Earth. This is considered 1 astronomical unit, 150 million kilometers. Now, as we're pacing out, I'm going to take one step. This is 15 million kilometers. So the Earth at 1 AU will be 10 paces from the sun. So we're going to take the Earth and move it out to 1 astronomical unit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're at Earth's orbit, 1 astronomical unit. And as you can see, Venus at 0.7 and Mercury at 0.4 astronomical units are closer to the sun. Now Mercury, because it's so close to the sun, has no atmosphere. All the atmosphere has been blown off by solar winds. And there's one peculiarity about Mercury is that it's too small it's too heavy for its size. And it spins the wrong way. So it's a puzzle in the solar system. Venus is a gas, has real thick gas clouds. It's about the size of Earth. And because it's so close to the sun, it's very hot, about 700 degrees Fahrenheit. Of course, the Earth, between -40 and +40 at the poles and the equator, it has a lot of water, a basis for life. As we move out to Mars, which is 1.5 astronomical units, Mars is got thin atmosphere, it's smaller than Earth, and its average temperature on a warm day is -70 degrees Celsius. Now, what we have here is the life zone of our star. That's the point around the orbit of a star where water can form, both as a gas. In the case of Venus, we have steam in the atmosphere. Mars, we have ice, water ice in the poles. And of course, Earth in the middle has both water and ice. It has a mix. So this is called, besides being the life zone of our star, it's also called the Goldilocks zone. Because as Goldilocks found out, the porridge was too hot and the porridge was too cold, but here the porridge was just right, where we find life on our planet. So we're in about the middle of the life zone of our sun, and this is where the rocky planets are, close to the sun. We're only 1.5 astronomical units away from our star when we reach Mars. Now that we've reached Mars, our next station on our journey is the asteroid belt. Now the asteroid belt stretches between 2.1 astronomical units and 3.2. So we're gonna position our marker here halfway in between. So we need another 10 paces, or actually another full astronomical unit from Mars, which is at 1.5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the center of the asteroid belt. Now it stretches from 2.1 to 3.2. And sometimes the solar system won't let us stand still. In the asteroid belt is roughly 100,000 objects, rocks, floating around the orbit of the sun. The two largest, Ceres and Vesta. Now, because of the change in what is a planet, Ceres is now considered a dwarf planet. It's 1,100 kilometers across. Vesta's around, I think, 750 kilometers across. But they're the two largest objects in the asteroid belt. So in the asteroid belt that circles the sun, we have over 100,000 small rocks of all different sizes that we know of. And they orbit around the sun in a fairly stable situation. Now, as you can see, looking back at the sun is looking a little smaller than it did when we were just at the Earth. Now, our next destination, of course, is Jupiter, the first gas giant. We've had all the rocky bodies in close to our star, and we're moving out to past the asteroids, which are originally thought to be the remains of a planet, but we know that there's not enough materials for that to have occurred. These are just pieces of rock left over from the formation of our solar system. So we're going to take Jupiter, we're going to move out to Jupiter, and to reach Jupiter, we're going to have to go another 25 paces. So basically, as far as we've reached the middle of the asteroid belt, that is how much farther we have to go to reach the planet Jupiter. More paces for Jupiter's orbit. '21, '22, '23, '24, '25, and we've reached Jupiter's orbit. Now, everyone knows that Jupiter is the largest body in our solar system next to our sun. It's 11 times wider than the Earth, and it's a gas giant. It has some features that everybody looks for. The Great Red Spot, which is a giant storm that's been there from our knowledge for at least 400 years. But one of the cool things with Jupiter is that you can see its 4 largest moons. They call them the Galilean satellites: Europa, Io, Ganymede, and Callisto. They can actually be seen in a pair of binoculars as a straight line of little tiny stars. And if you watch them over different nights or over the whole night, you can actually see those little stars change position because the moons orbit Jupiter. So even though Jupiter is 5.2 astronomical units away from the sun, we can still see the moons, the large 4 Galilean moons of Jupiter. Now, to go on from here, we're at Jupiter's 142 or 143,000 kilometers across, 11 times the size of the Earth. We're at 5.2 astronomical units, roughly 778 million kilometers away from the sun. Remember, the Earth is only 150 million kilometers from the sun. Now, to get to Saturn, which is at 9.5 astronomical units, we need to go another 45 paces. So that's a bit of a walk. Okay, we've moved out 45 paces from Jupiter. We're now at 9.5 astronomical units within our solar system. So we're 1.43 billion kilometers now from the sun. Saturn, of course, is a wonderful planet. It's 9 times the size, or 9 times wider than the Earth. The rings, as you learned with the moonwalk talk, are almost the distance between the Earth and Moon, 365,000 kilometers across the width of the rings. They're spectacular in a small telescope, very easy to see. Also, another object around Saturn is Titan, the largest moon in our solar system, the only moon with an atmosphere. We're out here at 9.5 astronomical units, and if we look back towards the sun, we can notice the change in the size of the sun, how small it looks compared to when we were at the Earth. And we'll move back into the solar system and just take a peek when we reach the Earth at the difference between the sun now and the sun when we return back on Earth. Now, unfortunately, we're in a football field, so we can't proceed any farther. But if we were to go to Uranus, the next planet, we'll have to walk this distance again to go to Uranus, this distance again from Uranus to Neptune, and this distance again to go to Pluto. So we're going to head back in towards Earth and just see how the sun gets large. Now, as we head back in towards Jupiter, keep an eye on the sun. You'll notice that it'll start looking larger. The sun will start looking larger as we get closer to the sun. We're moving in from Saturn in towards Jupiter again. We're going back another 45 paces back towards the sun. We're going from 9.5 astronomical units back to 5.2 astronomical units where Jupiter is. And you can see Jupiter's starting to get larger in the view. Very easier to see now. And the sun is starting to get a little bit bigger as well. Now, if we had a really large field or an opportunity to do it on the street, we could go all the way to Pluto and see if we could still see the sun. It might be awful small by then. But as you see, we reached Jupiter and we're heading up back through the asteroid belt, back towards Mars. It's getting a little warmer on the planet. And Mars is a nice warm summer afternoon at -70, around 110 below in the wintertime. And in the wintertime, the oxygen and water ice freeze out of and create the poles, the pole caps of Mars, both carbon dioxide ice and water ice. So we're now into the life zone of our star, the cold part of the life zone, back towards Earth. And as you can see, our sun looks very much larger from here at 1 astronomical unit than it did from way back at Saturn. Now, because of the size of the field, we can't walk to Uranus, Neptune, and Pluto, but we're going to take a look at the planets now and just go over a little bit of the information. So if we were to walk the distance to Saturn again, we would reach Uranus at 19.2 astronomical units. Now, Uranus is another gas giant, but the peculiarity about Uranus is that we don't see it this way. It's actually tipped on its side, and it was probably the fly that tipped it over. And we're actually looking through a telescope, we're looking at Uranus on its end. It was tipped over. They estimate about 3.5 billion years ago. And we know that because of the Voyager probe, when it went by, it measured the magnetic field and realized the magnetic field of the planet was tipped over almost 95 degrees. So it's tipped on its side and spinning this way. So we don't see many features, but this is the color you would see if you look through a small telescope or binoculars at Uranus. So we are twice as far as Saturn. So I don't know if we can take a quick look at how far Saturn is and how small it is in the field. We're twice as far as that right now when we're at Uranus. And you can see how far away Saturn was. Those rings are pretty tiny from this distance. But they still look pretty good in a small telescope. Now we're really getting out there. Going to Neptune is 30 astronomical units. So another 10 astronomical units past Uranus. So about the same the 10 times the distance from the sun to the Earth, again, after we reach Uranus to reach Neptune. Now Neptune is smaller. It's about 3.5 times wider than the Earth. But the puzzlement with Neptune, and what they think they figured out, is Neptune is very hot. Creates a lot of thermal activity inside the gas giant, and that creates very, very high winds. At the upper atmosphere, the winds they estimate to be roughly 1,770 kilometers an hour, about 1.5 times the speed of sound. So those winds in Neptune are moving really, really fast. Now, some of us grew up with Pluto as the 9th planet, found in 1930 by Clyde Tombaugh. But recently it's been demoted. And there's some various reasons for that, but mostly science needs a definition. So we need to know what we see when we look out. And we found planets around other stars since 1995, and we found other bodies the size of Pluto. Now these models are a little bigger so we can get some detail, but New Horizons 2 years ago went out to Pluto at 39.5 astronomical units. Now Pluto's orbit actually comes in just inside Neptune's orbit and then goes way out. So right now it's about halfway out to the farthest point in its orbit. It has a very strange elliptical orbit. But Pluto, as we found out from New Horizons, is actually a dual planetary system. This point here, in between the two, is where both the moon Charon, or what we thought was the moon, and Pluto rotate. So these are actually rotating about this point here. They both orbit the same point. So this is a dual planetary system, even though they're both dwarf planets. But what is unusual is that they both have cryovolcanoes, and where the energy comes to produce volcanoes that far away from the sun is still a mystery. Something for the young people to hopefully discover. New Horizons has continued out and has found other dwarf objects, and we're still continuing out, still exploring our solar system. But our walk here, if we pace out, we went 395 paces. So full strides, 15 million kilometers a pace. 395 paces to reach Pluto. So our solar system is fairly big. But the next step is how far is the nearest star? And that, the distance to the nearest star, we measure in light years. And light years is 10 trillion kilometers in 1 year. So 1 light year is 10 trillion kilometers. Here, 1 astronomical unit within the solar system is only 150 million. So it's the next step up looking at the stars. And of course, most of you know that the nearest star is 4 light years away, Alpha Centauri. So that will be the next one, but I don't think I'll be able to do that in the field. I'll have to get a rocket ship and work on that. Thank you, everybody. And if you have any questions, please forward them.
There. Thanks, Paul.
Okay, just to sort of re-emphasize, I don't know if you can see the black point here is the center of gravity of the Pluto-Charon system. So the rotation is around the center of gravity. And we knew this because the images they took from 1 million kilometers showed the all sides of Pluto and Charon. And that was a surprise because they thought they'd only get pictures from one side as the New Horizons passed by. So a lot of new discoveries with the New Horizons in the solar system. A lot more to be discovered all the time. So,
yeah. Just as a matter of note for our attendees and those that watch this video in the future, that video that we just showed you is actually on our RASC Halifax YouTube site. So if you didn't get a good reception on your end, you can certainly watch it much better on our YouTube site. It'll be a lot clearer for you. So again, thank you very much. It's kind of cool to see how you did all that. And I know the effort and the excitement that that generates when we present it at any of our events. So thank you so much for this, Paul.
yeah. Well, I encourage anyone that has a garden center nearby or a pool center to get the materials and try to put it together yourself. Feel free to email the Halifax Center. They'll pass it on to me if you need more details. But definitely, if you're doing any for the teachers, models of the solar system are very easy to make, and it's one of the classes I did over the years. They actually had the students make the models themselves. So it's a great project. And there again, the more hands-on, the more detail you can put into the model, the more fun that the kids and participants will have, and the more hopefully they will learn.
And in fact, you actually had at our last Nova East, you actually had the kids make their own Mars models And
Yes.
it's one of the youth activities. So
Yeah,
that's something
they
can do
started
very
from
easily.
scratch and did all the steps that I did. And we used Mars Global Surveyor, the images from Mars Global Surveyor to paint the pictures of Mars on the styrofoam balls.
Okay. Well,
Yes.
thank you. Oh,
Someone-
sorry. Is there a question?
Yeah, Paul, would it be helpful to somehow, with the Pluto and Charon models, is to put the stick that kind of goes down, going into the dowel at the mid spot, and so
Well,
that
if
them are
you,
actually moving around?
yes, if you could, the only problem is I connected them with a little tiny toothpick and a score, so the size difference. But yes, that would probably be better if you could connect it at the point of
At the point.
rotation. Yeah.
So you could really
so-
see that, yeah.
Yeah, but
Okay.
I sort of just went with the Pluto and attached Charon so that it wouldn't fit in a little person's mouth. So that's why it's not there. It's because I was trying to keep it from being eaten again. It's
Good idea.
but yes, that would be more visually accurate to connect it at the point of center of gravity.
Okay.
So,
Given there aren't any questions in the chat at this point, I think we'll close here. Again, many thanks to Paul for today's presentation. Next Tuesday, September the 8th, we have Pat Kelly joining us for his presentation on Mars, all about Mars, the science of what you're seeing. He's going to give us a little bit about what we know about Mars and what you can expect to see during the October observing of it, given it's going to be it will be at its closest to us at that point in time. If you aren't already a member of RASC, please, we encourage you to do so. There's lots to see and do with our organization and lots of perks and benefits along with it. So in the meantime, thank you all from coast to coast for joining us. And again, thank you to Paul, and we'll see you all next week.
right. Thanks, everybody.
Bye-bye.
Bye-bye. Thanks,
Bye.
Paul. Thanks, everybody.
Mhm.